just gave our agentic swarm the ability to see. Now we have to teach it how to hear. In the cognitive architecture mapped out in Imran Ahmad's 30 Agents framework, this capability belongs to Agent 20, the audio processing agent. Agent 20 moves beyond simple transcription by treating the acoustic waveform as a primary data source for reasoning, extracting features that text strings alone cannot represent. While visual perception analyzes a static, spatial grid of pixels, auditory perception has to process a continuous, unfolding temporal sequence. Without a native way to process that temporal data, an enterprise swarm is functionally deaf to human nuance. Imagine two people saying the exact same sentence. "I have been waiting all week." One is practically bouncing with joy. The other is gritting their teeth, preparing to file a complaint. When you feed both of those recordings through a standard automatic speech recognition pipeline, the filter strips away the physical sound. Both waveforms are flattened into an identically sterile string of text. That standard cascaded pipeline completely discards prosody. It erases the pitch, the rhythm, the hesitations, and the sarcasm. As a result, the downstream large language models tasked with handling the customer fail to detect true human intent. They are starved of the acoustic metadata that carries the actual meaning. Bridging this information gap involves an architecture designed to extract both semantic content and the nonverbal prosodic features, typically lost in transcription. To achieve this, Agent 20 operates on a formal sense, model, plan, act loop. This diagram outlines the architecture. Raw audio enters as a messy vector of bytes. The agent applies root-mean-square normalization, ensuring consistent input energy. The waveform is then encoded. Convolutional layers downsample the input, and transformer layers convert it into a MEL spectrogram. This rigorous physical grounding at the base of the pipeline prevents the agent from hallucinating or being confused by ambient volume differences before the reasoning process even begins. Once encoded, the architecture splits. The data flows down two parallel processing streams to capture both dimensions of speech. The top branch is the content path, where a deep learning model executes semantic transcription, translating the spectrogram into raw words. The agent then applies a mode-aware text cleanup strategy. If the context is a legal record, it runs in verbatim mode to preserve every stutter. If generating meeting notes, clean mode strips out the disfluencies. This Python code shows how the semantic output is strictly typed. Data classes lock each transcribed segment to precise start and end times, generating a mathematically usable map of the dialogue. Meanwhile, the parallel affect path ignores semantics entirely. It analyzes the raw acoustic features of the voice itself, extracting the mean pitch, rhythm, pitch variability, and vocal energy. Those prosodic features are mapped onto a continuous three-dimensional grid known as the valence, arousal, and dominance space. This quantifies the exact emotional profile of the speaker. Keeping the content and affect paths strictly parallel ensures that semantic bias cannot override the acoustic reality of the recording. Recombining these two streams cannot be left to probabilistic guessing. The agent requires deterministic logic to draw conclusions. The two branches finally reconverge at the crucial reasoning stage. The system uses a strict chain-of-thought prompt structure, which you can see in this function. It forces the language model to systematically identify acoustic segments, examine specific prosodic cues, and weigh the evidence before diagnosing an emotional state. For this logic to be reliable, the pipeline demands deterministic decoding. The agent sacrifices creative variation to guarantee absolute reproducibility in its outputs. You can see this enforced in the code by setting the sampling parameter to false. The model must select the highest probability token at every single step. Finally, the agent packages the results into a structured payload. This single object contains the clean transcript, temporal confidence scores, and the quantified emotional profile. This architectural rigor yields a verifiable audit trail rather than a stochastic guess, producing an output that is safe for downstream enterprise deployment. In a live call center environment, this dual-path payload is highly actionable. If a user's acoustic data triggers an arousal spike on the affect cath, the system immediately routes the angry caller to a human manager. In compliance-strict medical or legal environments, the verbatim transcription mode provides an unedited, time-stamped record required for audits. Upstream systems consumes this empathy-aware payload directly. A conversational agent can dynamically adjust its dialogue tree, responding with tact when it detects frustration. A verification agent uses the temporal confidence scores to flag specific, low-probability audio segments for manual factual review. Agent 20 acts as the high-fidelity perceptual front-end. It turns raw noise into actionable intelligence for the rest of the swarm. The architecture does have strict boundaries. Because it processes discrete audio clips through a heavy chain-of-thought reasoning loop, it struggles with the ultra-low latency required for real-time conversational duplexing. There are also severe ethical hazards. Deploying heuristic emotion surveillance without user consent or human review carries significant legal and moral risks. To truly interact with the world, the swarm must step out of the audio and visual domains. It must move beyond discrete perceptual signals and tackle the continuous, asynchronous streams of environmental telemetry. Processing those live, heterogeneous sensor streams requires a distinct architecture, Agent 21, the physical world sensing agent. You can explore the complete Python implementation of the audio processing agent in Chapter 11 of Imran Ahmad's 30 Agents Every AI Engineer Must Build, and visualize the entire stack at neuralsca. Extracting the affect behind the words provides the context needed to ground an agent's response in the technical reality of the user's intent.